Number 1, Keisha's kitchen is shaped like a square. The room has an area of 225 square feet. What's the length of one side of Keisha's kitchen? So to answer this question, you have to know that the area of this room is 225 square feet and that is shaped like a square. So you have to know the length of the area of a square is equal to length times width, and the length and the width are exactly equal to each other. So the area of a square is equal to side times side, which is equal to side squared. So we know that the area, is side squared, which is also equal to 225. We want to find the length of just one side, so we'll take the square root of both sides because the square root is the inverse of squaring a number, which is here where we squared our s, the length of the side. So the square root of s squared is s, and the square root of 225 is 15. So the length of one side is 15 feet. And we move on to number 2. Simplify 4 squared to the third power. So 4 squared to the third power really, of course, is the power rule. And that means that if you have one base and 2 exponents, you multiply the exponents. But for those who are a little confused about it, 4 squared to the third power, just you treat this 4 squared as if it was any other base. So you multiply the base times itself 3 times. And then you see, oh, well, that's 4 squared times 4 squared times 4 squared. And this gives us the product rule, which means we keep our base the same and we'll add our exponents. So our solution here for number 2 is D. Moving on to number 3, consider the number 0.49 repeating. Write 0.49 as a fraction. So the first thing we will do is we'll set x equal to 0.49 repeating. Then we look and see, well, what's the last repeating digit? And that digit is 9 because it's the one that repeats last. And this 9 is in the hundreds place. Since it's in the hundreds place, we're going to multiply both sides by its place value, which is 100. So we'll multiply the left side by 100 and the right side by 100. This will give us our repeating decimal behind the decimal point, of course, or our repeating digits behind the decimal is a better way to say that. And then we're going to subtract off our original value because we want to get rid of our repeating digits. And once we do that, we have 100x minus x, which is 99x, and then 49.49 repeating minus 0.49 repeating. Those repeating digits finally cancel out, and you're left with 49 minus 0, which is 49. And finally, you'll divide both sides by the coefficient 99, and you're left with x equals 49 over 99, which cannot be reduced because because 49 and 99 have no other factor in common. So this is our solution here for part A. 0.49 as a repeating as a fraction is 49 over 99. Part B says, is 0.49 repeating rational or irrational? And it's obviously rational because 0.49 repeating can be written as a ratio of 2 integers. And because it is a repeating decimal. We'll say it that way. It's a repeating decimal. And we know that we have a way to write repeating decimals as fractions. And that's it for number 3. We'll go ahead and move on to number 4 on the next page. All right, a cube-shaped paperweight has a volume of 216 cubic centimeters. What's the length of the paperweight? So we have this paperweight that's in the shape of a cube. So we have this cube, Inside the cube, we have 216 cubic centimeters. So with a cube, the attributes of a cube are that all the sides are the same length. So we have side times side times side, similar to the square, but it's volume. So we know volume is length times width times height. So the volume of this cube is going to be side times side times side, because all the sides have the same length. And that's going to be equal to 216 cubic centimeters. And we know we can rewrite s times s as s cubed equals 216 cubic centimeters. And again, just like one of our previous problems where we found the square root of the area to find the length of the side, we'll find the cube root of the volume to find the length of each side, because that's the inverse of cubing a number. So the cube root of s cubed is, of course, s, and that's equal to the cube root of 216. And of course, this means what number sorry, multiplied by itself 3 times equals 216, and that number is 6. And of course, we're talking about centimeters cubed, so even if you take the cube root of centimeters, that'll give you centimeters. All right, and that is 6 centimeters, and that is our C. Number 5, look at the equations below. Tell whether each equation is true or false. All number 5 is quizzing you on the exponent rules. All right, A, 4 to the 0 power to the 6 power. This is the power rule. And I'll go ahead and write that underneath. Power rule says keep your base, which they did, multiply the exponents. 0 times 6 is 0. So 4 to the 0 is not equivalent to 4 to the 6th power. So that's false. B, 3 to the 8th divided by 3 to the negative 2nd is equal to 3 to the 10th. This is the quotient rule. Quotient rule says if you have two numbers, you're dividing them, they have the same base. You keep the base the same, subtract the exponents. So they're doing 8 minus negative 2, which is keep, change, change. Keep the first number the same, change subtraction to addition, change the second number to its opposite, and you're left with 10, which is exactly what they have, 3 to the 10th power, true. C, we have the product rule. Product rule says if you have the same base and you're multiplying these two numbers, keep the base the same, add the exponents. So you're supposed to do negative 5 plus 3, which is negative 2. So you would have had 2 to the negative 2nd power, but they have 1 over 2 to the 2nd power. So what they did here was then they invoked the negative exponent rule. The negative exponent rule says I can give you a number raised to a negative exponent and change it to a positive exponent by giving you the reciprocal and the opposite exponent. So the reciprocal of 2 to the negative 2nd power, everything, if it doesn't look like a fraction, you just put it over 1. The reciprocal would be 1 over 2 to the 2nd. And I know it's 2 to the 2nd power, the positive 2nd power, because I just give you the opposite exponent, and that is true. And moving on to D, this is the different bases, same exponents though. They have a different base, same exponent. When you have the different bases, the same exponents, you multiply the bases, but you keep the exponent the same. Something has to remain the same. And what's been common is that you keep what's the same. Okay. So it should have been to the 4th power 6 times 3 as the base. So it should have been 18 to the 4th. But they kind of combined the different base same exponent rule and the product rule, and you can't do that. Okay, you do one at a time. So they should have just multiply the bases and kept the exponent the same, but they didn't. So that's false. Number 6, in a lab, a scientist is growing bacteria for a study. The scientist begins with a bacteria population of B cells. She discovers that after 3 hours, the population of bacteria is B squared cells. 3 hours later, the bacteria population is B cubed cells. If the population of the bacteria after these 6 hours is 1,000 cells, what was the population at the start? And explain how you found your answer. So, the first hour, hour 0, it was B to the 1 power, basically. It was just B, so it's B to the first. The third hour, or the next time, the next cycle, it was B squared. Then it was B cubed, and we'd assume it would keep happening. So they tell us that B cubed was equal to 1,000. So then you're supposed to find out, well, what is it for the first one then? Well, if B cubed equals 1,000, we know we can find just B by doing the inverse operation. So right now, we have B being multiplied by itself 3 times. So we can do the inverse of cubing a number, which is finding the cubed root of a number. And if we find the cube root of B cubed, we have to find the cube root of 1,000. So B cubed, the cube root of B cubed is just B, because the cubing a number and finding the cube root of a number cancel out each other, and you just drop down your base. And then the cube root of 1,000 is actually equal to 10, because 10 times 10 times 10 equals 1,000. Okay, I'll put 100 equals 1,000. So what number when multiplied by itself equals 1,000? Multiplied by itself 3 times equals 1,000, and that's 10. So it was 10 cells in hour 0 when they started off the growing bacteria, when they started doing that. So it was 10 cells. And we just use inverse operations here. And sorry about that, I got a little tongue-tied. Number 7, simplify 9 to the 0 power. This is the 0 power rule. And the 0 power rule states that any base, unless a 0, when raised to the 0 power, is 1. So 9 to the 0 power is just 1. Okay, that's your answer here, 1. All right, and we go ahead and move on to number 8. Consider these numbers: 3.21 repeating, pi 3.5, and the square root of 8. Which of these numbers are rational and explained for part B? For part A, which of these numbers are irrational and explained for part B? All right, so a rational number is, it can be a repeating decimal, an integer, a whole number, a natural number. Okay, something like that. Okay, and an irrational number is a non-repeating, non-terminating decimal. Okay? All right. So, looking at what a rational number can be, we know that 3.21, and we'll go ahead and say a rational number is any number that can be written as a ratio of 2 integers. Okay, so 3.21 fits this bill because it is a repeating decimal, and 3.5 is also a part of this because it can be written as a ratio of two integers. And I know that because 3.5, I could write it as 3 and 5/10, which can be reduced to 3 and 1/2. And I know that 3 and 1/2 or 3 and 5/10 is just, sorry, I was going backwards. I know that I can rewrite this as 3 times 2 plus 1, which is 7/2. And this, of course, is a ratio of two integers because 7 is an integer and 2 is an integer. Same thing I can say for 3.21. I know that 3.21 repeating will be 3 and 21 over 99, which of course I can simplify that, but I can then just change my mixed number to an improper. I can do that, and I know that if it can be turned into a ratio of two integers, which of course a mixed number can, and this terminating decimal can, so let me add that as well. That I know it's rational. Okay, 3.5 is a terminating decimal, while 3.21 repeating is a repeating decimal, and we know the trick to turning those into fractions. Okay, then we move on to part B. So the ones that are irrational are, of course, pi and the square root of 8. So we have pi and the square root of 8. Pi is irrational because it's non-repeating and non-terminating. It just keeps going on forever and ever and ever and ever with no pattern. Okay, so that makes it irrational. The square root of 8 is irrational, however, because once we throw in the square root, the square root of a number can only be rational if the number inside the radical is a perfect square. 8 is not a perfect square. Okay. And I'll write that out as well. And when dealing with square roots, a number will be rational only when the number inside the radical, or let's say under the radical, is a perfect square. Okay. So then part C says label the number line and graph the appropriate or approximate location of each number. So we know that pi is about 3.14. We'll just say it there. We'll just go ahead and approximate that number. And the square root of 8 is super close to the square root of 9, which is 3. So it's a little bit below it. Okay. And that's about 2.8. So it's not equal to it, but it's there. And then 3.21. We don't have to do anything with that. That was dumb. Okay, so then we have the decimal approximations for these and the, yeah, so we're good there. So we know that our numbers are between, we'll just have it be over here about 3.5. So we'll have it between 2. 2.3, I'm sorry, 3 and 4. Let's get it. So we have 2.2, 2.4, 2.8, 2. Oh, sorry, I skipped 2.6. And then 3.2, 3.4, 3.6, and 3.8. All right, so let's go ahead and start off with 3.21. We know that's going to be very close to 3.2. So we'll have it here. I'll use a different color. This is our 3.21 repeating. Then we have exactly 3.5, which is going to be exactly between 3.4 and 3.6. Then we have pi, which is 3.14. That's going to be very close to, very close to 3.2. That's going to be our pi. And finally, we have our square root of 8, which is around 2.8. So it is just a little bit above 2.8, so we'll have it here. And that's our square root of 8. All right. You didn't have to label your number line exactly like I did. This is just what I wanted to do. All right. And then we'll move on to the last page, 9 and 10, or the last page to answer questions 9 and 10. Consider the square root of 15. Approximate square root of 15 to the nearest integer and explain how you got your answer. So I would approximate the square root of 15 to be between the square root of 3 and the square root of 4. So, I'm sorry. So that's so wrong. Not between the square root of 3. Between 3 and 4, because the square root of 16 is 4 and the square root of 9 is 3. I said that so backwards. I'm sorry. So I know that to the nearest integer, the square root of 15 is really close to the square root of 16, because 15 or 9 is only 6 away from 15, while 15 is only 1 away from 16. So I would say it's way closer to the square root of, or to the square root of 16. So it's way closer to 4 than it is to 3. And all you have to do to figure this out is you can just find the perfect squares that are right above it and right below the number you're trying to approximate. Sorry. So you have your perfect square, square root of 1, square root of 4, square root of 9, 16, 25, 36, and so on and so forth. And your square root of 15 lies about here. So that's way closer to the square root of 16, which is equal to 4. Okay. Part B says approximate the square root of 15 to the nearest tenth. So what we would do is, since I said in part A that it's really, really, really close to the square root of 16, it's literally only 1 away, I'll go ahead and start off my approximation being about 1/10 away from the square root of 15, and I'll go 1 below it. Sorry. Yeah. So I'll go, 1 below the 10th power away, or the 10th place away, and 1 above it, which is not really helpful. And I did it wrong again. Sorry. So I've got, let me try 3.7, 3.8, and 3.9. All I'm going to do with these numbers is square them. And I'll just go ahead and square these numbers. 3.7 squared is 13.69, which is a little off, so we don't want that one. 3.8 squared is 14.44, which is close. And then 3.9 squared is 15.21. So the one that's closest to 15 is, of course, 3.9, because it's only 0.21 away. This one, 3.8 squared, is 0.56 away. And the other one is a whole 1.31 away. Okay, and that's just way too far. So the closest distance is 3.9 squared. So when I approximate the square root of 15 to the nearest tenth, I'm going to approximate it to 3.9. And that's how I got my answer. I just proved, this is all my proof here. Part C says label the number line and graph the approximate value of the square root of 15 that you found in part B. So I know it's between 3 and 4, which again, I already knew that because I used my perfect squares to help me out with that, and I just located between which two perfect squares it lay between, and that was 3 and 4. So I'll have my 3 and my 4, and of course I'll have it broken into tenths. So 3.1, 2, 3, 4, 5. I like to make this one a little bigger if I can because it helps me know where my halfway mark is. All right. And then I said that the approximate value of the square root of 15 was about 3.9. So, and it went over a little bit, so it's probably a little bit under that. So I'll just go ahead. And they said, well, it's probably going to be a little bit under that. But they told me to just put it to graph my approximated value, which was 3.9 exactly. So I'll say that's about the square root of 15 is about 3.9. And I'll just leave it like that. And finally, number 10, which expressions are equivalent to 5 to the 18th power, and choose all that apply. So you're going back to your to your exponent rules again. Okay, A is referring to the product rule. You have two numbers multiplied together, both have the same base, different exponents. You should keep the base the same and add the exponents. So that's 5 to the 11th power, which is not the same as 5 to the 18th. Then you have the quotient rule, of course. Quotient rule says when you're dividing two numbers with the same base, you keep the base the same and you subtract the exponents, and you would get 5 to the 18th power. So B is true. C again is our product rule. I'll just put PR. And you keep your base the same and add your exponents, and you would get 5 to the 18th power. So that's true. D, 5 to the negative 18th power. You can clearly see that is not the same. The exponents are not the same, and when you have one is positive, one is negative, they don't have the same value. This was actually equal to 1 over 5 to the 18th power, which is way smaller, and of course the inverse of 5 to the positive 18th, so no. And then finally you have E, which is the power rule. Power rule says if you only have one base but two exponents, keep your base the same and multiply your exponents. So this would have been 5 to the 77th power, which is of course not equivalent to 5 to the 18th power. And there you go.